Systems of equations, the first lesson, developing systems of linear equations. Now we know what a linear equation is. It's a straight line. A cage at the Calgary Zoo contains only flamingos and zebras, with a total of 30 eyes and 44 feet. Okay, so what do we know? We know that flamingos have 2 eyes and 2 feet, and zebras have 2 eyes and 4 feet. So if there are 30 eyes, then there could be 15 flamingos, or there could, and no zebras, or there could be 15 zebras and no flamingos. And I guess really what that means is there's a total of 15 flamingos and zebras, right, which will give us the 30 eyes. And we need some way to figure out the 44 feet, and we know that zebras come with 4 feet and flamingos only 2. So assuming there are no deformities, missing parts, or extra parts on the flamingos or zebras, how many of each animal do you think are in the cage? So we have to kind of figure this out. Well, there would be... Will there be more zebras? Well, let's see. If there were 10 zebras, that would give us 40 feet, and then 5 flamingos would give us 10 feet, and that's too many. If there were 8 zebras, we'd have 32 feet, and then another 14, which is 46. That's too many, so let's go with 7 zebras. 8 flamingos, right? We know we need a total of 15 animals, which will give us the 30 eyes. This will give us 16 feet, and this will give us 28 feet, which is the 44 feet. Alright, well, we can't necessarily always puzzle out every question that way, so we can use a model involving a system of equations that would allow us to verify our answer to the question above. If we let f be the number of flamingos and let z be the number of zebras, then we need 2 equations. That's what a system is. It's more than one equations. More than one equations. Nice. So we know that every flamingo has 2 eyes, so 2 times the number of flamingos plus 2 times the number of zebras will equal the total number of eyes. We know that flamingo have 2 feet, but zebras, or zebras, have 4 feet, so 2f plus 4z will equal 44. Use these equations to verify your answer. Now, verifying an answer means to plug in. So if we start with the equation 2f plus 2z equals 30, we put in 8 for flamingos and 7 for zebras, we get 30. Now this right now is an assumption, right? 16 plus 14 equals 30. 30 equals 30. So this sentence is true, right? If we had the wrong number of things, if we had like 10 flamingos and 5 zebras, we'd get 20. 10 flamingos and 5 zebras. Actually, 10 flamingos and 5 zebras would work. I think any number that adds up to 15 would in fact work. But if we had 20 zebras or something, you know, this would not be a true sentence. Now, in order to be the solution, it must not only be true, because any pair of numbers adding to 15 for f and z will make this true, but only one of those pairs of numbers will also make this one true. 2 times 8 plus 4 times 7 equals 44. Sometimes you might want to put a little question mark over that to just say, is this true? 16 plus 28 equals 44, right? I'm not sure. And 44 equals 44. Also true. Since it's true for both equations, then it satisfies the system of equations. When taken together, the 2 equations relating the number of flamingos and zebras with the number of eyes and feet is an example of a system of equations. A system of equations is a set of equations that are considered together. Now, this could be 2 or more equations. In this unit, we will work with systems of 2 linear equations. Right? In future courses, you'll do more than 2 and not necessarily linear. A solution to a system of equations is a pair of values that satisfy both equations. satisfies, I'm not sure which, but satisfy or satisfies both equations. Examples. Okay, so the rest of this is examples. A school district has small buses that carry 12 passengers and large buses that carry 24 passengers. The total passenger capacity for all the buses is 780. There are 20 more small buses than large buses. What unknowns do we want to find? Define variables for those unknown values. So the first step is always figuring out, and I guess what's in here is how many of each. How many of each type of bus? Okay, so first step in solving any system, or really in developing any equation, whether it's a system or not, is to define your unknowns. So let S be the number of small buses. Let L be the number, and you should use letters which are evocative of what it is you're trying to find. In a sense, it doesn't matter. You could let X be the number of small buses and Y be the number of large buses, but if you can, a little mnemonic, in the sense of S for small and L for large. Create a linear system to model the situation. So linear system. What have we got? It has small buses that carry 12 passengers. So 12 times the number of small buses. This will be the number of passengers that fit on a small bus. Plus 24 times the number of large buses is equal to 780. There are 20 more small buses than large buses. So the number of small buses, there are 20 more of them than large. So we're going to take the large and add 20. And sometimes when you're figuring out your equations, you always want to go back to the wording and just see if that makes sense. Like if you said, if there are 10 large buses, then how many small buses? Well, there are 20 more, so there will be 30. So if I put a 10 in for L, I get a 30 out for S. Just a way to verify that you, in fact, set this up correctly. You are told that there are 35 small buses and 15 large buses. Use the linear system to verify. All right, well, let's start with the easy one. There are 35 small buses and 15 large buses. So the first, actually the second equation is satisfied. And now, what's formula? Remember math, it's formula. Substitution, there are 35 and 15. I'm going to do the question mark thingy this time, right? We're not sure. Is this true? I'm not sure. Let's find out. Okay, 12 times 35. Well, 10 times 35 is 350, and 2 times 35 is 70, so that will be 420. 10 times 24 is 240. 5 times 24 is half of 240, which will be 360. Actually, 120 plus 240 is 360. Is this true? 780 equals 780. Yeah, let's put a little check mark to say, yeah, this is true, right? That is a true. So both of these statements are true, meaning each equation models the situation given the system of equations, right? More than one equation is a system, models the problem, and it's all good. Just throwing that in because I accidentally. A school raised $195 by collecting 3,000 items for recycling. The school received 5 cents for each pop can and 20 cents for each large bottle. What unknowns do we want to find? Well, probably the number of pop cans. Define variables for their unknown values. So when you're communicating a solution, you have to set something out for people. You can't just rush into equations. Nobody will know what anything is, even if it's sort of obvious. So let C be the number of pop cans. And these are just statements, right? Let B be the number of large bottles. Bottles. Now, you could equally likely have used P for pop cans and L for large bottles. It doesn't really matter. The school collected $195. So we've got dollars and cents. So what we want to do is we're going to change 5 cents into 0.05 dollars. And we're going to change 20 cents into 0.20 dollars. This way we're working in the same units, right? It's either that or we change $195 into 19,500 cents, which makes no sense. Well, makes too many cents, so we'll stick with dollars. Okay, we know that each pop can is worth 5 cents, so 0.05 times C is the number of dollars that were collected for pop cans. And actually, before we do that, we should model, so let's just move this down. We should model the fact that we collected 3,000 items for recycling. So C plus B, the number of cans and the number of bottles, is 3,000. The value of each can is 0.05 times C. The value of each bottle is 0.20 times B, and the total value of cans and bottles is 195. The school collected 2,700 pop cans and 300 large bottles. C plus B is 3,000. So the first equation deals with representing the number of items. 2,700 plus 300 equals 3,000. 3,000 equals 3,000. So number-wise, we're good. The other equation, which we are going to write out in its entirety, and then we're going to substitute. So at this point, this is like a formula. 0.05 times 2,700 plus 0.20 times 300 equals 195. This is kind of obvious over here, right? We can see that that's going to work. Here, this is not so obvious. So I'll put a question mark. Either one, it doesn't matter. If this doesn't work, you're just going to reject the solution. You're going to say, well, no, this doesn't match the situation. Okay, well, if it were 10 cents, that would be $270, so it will be half of that. I really shouldn't put in the units here, right? We use units at the end. So, okay, if it's 10 cents, it would be $270, but it's 5 cents, so it's half of that, 135. And if this were 10 cents, this would be $30, but it's twice that, so that's 60. And at this point, yeah, it's kind of obvious. 195 equals 195. Check. And pause for phone. A store sells wheels for roller skates in packages of 4 and wheels for inline skates in packages of 8. A situation about wheels was modeled by the linear system below. Now, explain the meaning of each variable. So, probably I is the number of inline skate wheels. I. Actually, wait a sec. No, if this is 8i, this would be the number of wheels. So I is the number of inline skates. Number of inline skates. And R is the number of roller skates. Write a problem that is modeled by this. Okay, so we have a total of 80 sets of skates. So there is or are. There is a total of 80 pairs of skates. Some of which are inline, and some of which are roller skates. So that gives us our first equation. Now this would be, well, we need to tell each inline skate each inline skate. Now if we're going to get 8i, I mean each inline skate takes 4 wheels, but we should probably go with each pair. So let's go each. Oh, I can't split them. Okay, each pair of inline skates. Seeing as skates travel in pairs, each pair of inline skates require 8 wheels. Each pair of roller skates require 4 wheels. We have, or there are, a total of 440 wheels. There are a total of 440 wheels. Determine the number of each type of skate. Okay, so kind of working forwards from the numbers. So the other situations we dealt with, we would have been given this. In general, in math, the last sentence is what is it we're trying to find here, right? And that helps us define our variables. So in this case, what types of skates? That would be the I and the R. You know, so let I be the number of inline skates. Let R be the number of roller skates. There are a total of 80 pairs of skates. And that's not really true. There are a total of 80 skates, some of which are inline skates and some of which are roller skates. You know, we have to refine this a bit. So 4R, this is 4 times, but not necessarily the number of roller skates, right? Because it's a pair of roller skates would take 4 wheels, and a pair of inline skates would take 8 wheels. Pair, right? So this is pairs then. Wow. Pairs of, so the number of, cross off, I, number of pairs of roller skates, pairs of inline skates, and the number of pairs of. So sometimes going back and looking things over helps us to refine our thinking and our situation. Determine the number of pairs of each type of skate. A hot dog stand sells 3 hot dogs and 5 drinks for $21. 4 drinks and 6 hot dogs cost $24. Is the system of linear equations shown correct? Okay, 3 hot dogs, 5 drinks, 21. 4 drinks, 6 hot dogs. No. So 6 hot dogs plus 4 drinks. So no. And what do the variables represent? So H is the number of hot dogs. D is the number of drinks. And now we have a fixed system of equations, system more than one equation, right? For us, two equations, both linear. And these are like standard form equations, right? Remember, a standard form equation looks like this: ax plus by equals c. Determine if the point negative 10, 1 satisfies, that is the solution to either one of the systems of equations. A solution to a system of two equations is a pair of values that satisfies both equations. So let's start with, here I'm going to show you a different form of verification. This is called a left side, right side. So what we do is we make what's called a t-table. Because it has a T shape, and we take the left-hand side of the equation, 2x plus 7y, and we take the right-hand side of the equation, and right-hand side is negative 13. What we then do is we substitute, so 2 times negative 10, so that's the formula, this is the substitution, plus 7 times 1, and we just work out each side independently. Negative 20 plus 7 is negative 13, and that checks. And now we can check the next set of values. So left side is equal to negative x plus y, and the right side is equal to 9. Substituting, we get negative 10 plus 1, which is 10 plus 1, which is 11. So we say no, it does not satisfy, right? It satisfies this equation. This point is on this line, but it is not on that line, so it's not a solution. And as we look at graphical, we'll see what that means. And over here, the left side is x. The right side is 3y minus 13. The left side is negative 10. The right side is 3 times 1 minus 13, which is 3 minus 13, which is negative 10. So that's true. And now we're going to check the other one. So the left side is y minus 2x. The right side is 21. The y value, and remember, watch your variables, because these were x, y, this was x, and then y. This is y minus 2x, so y is 1. Minus 2 times negative 10 is 1. Minus negative 20, or plus 20, is 21, and that checks. So the point negative 10, 1 satisfies this equation, this equation, this equation. It therefore satisfies this system of equations, does not satisfy this equation, and therefore is not a solution to this system, but is a solution to this system. Is the system of equations defined by y equals x squared plus 3 and y equals negative 3x plus 2 a system of linear? No. Y equals x squared plus 3 is not a linear equation. And there we go. That'll do it. And that'll do it.